Hi viewers, in this video we will do another problem which was asked in GATE. In this particular question, they are asking for the differential equation governing the vibrating system which is shown over here. You can see here there is a point mass little m which is attached to a damper as well as a spring. Now we need to arrive at the differential equation governing this vibrating system. So as I always say, pause the video, try solving the problem on your own. Once you are done, then play the or see the rest of this video. We know there are a couple of ways in which we can arrive at the governing differential equation of a particular system. One is the Newton's second law. The second method is conservation of energy. Then there is methods like Rayleigh's method and all those. For this particular example, I will be using Newton's second law. So in order to do Newton's second law, I should have a free body diagram. Before that, let me tell you or brief you a few things. Let's say I have a spring over here and I'm fixing it over here, and then I'm pulling this point by an amount, say delta, and let's say the stiffness of the spring is K. Then if someone asks me what is the amount of force developed in this particular spring, then I can say it is F equal to K into delta. Pretty straightforward, because the net displacement or for this particular spring is delta. Now think of another case. The same spring with a stiffness delta. This time I'm pulling this end by an amount y, and I'm pulling this side by an amount x. Or in other words, sometimes y can be 5 centimeter and x can be 2 centimeter. Now again the same question. What is the force in the spring for this particular state, in which compared to the first case, this particular end is no longer fixed. It has a displacement x. Then the force in the spring will be K times the relative displacement, which is y minus x. Make sense? The same thing applies to a damper as well. Let's say I have a damper connected between 2 points, and it's this particular point is moving with a y dot velocity, and this point, let's say x dot. Then the force experienced in the damper will be given by coefficient of viscous damping will be C, then y dot minus x dot. It's pretty much common sense. The force experienced in each of these individual elements, doesn't matter whether it's a spring or a damper, it will be a function of the relative displacement, or it will be a function of the relative velocity between the two ends of the element, the two ends of the spring and two ends of the damper. Okay, so enough with the theory. Now, having seen all this, now it's time to apply whatever we have just seen in this particular problem. So let's go ahead and draw the free body diagram of this little mass over here. Then before that, so what will be the force in the damper? Force in the damper will be C into x dot minus y dot, because this point is seeing a displacement of x. That means the velocity of this particular point will be x dot and velocity of this particular point will be y dot. So the net force on the damper will be C times x dot minus y dot. Then what is the relative displacement the spring is seeing? This end is this particular end of the spring is fixed and this end is moving in this particular direction by x. That means the relative displacement is x or minus x, whatever it is. So the force will be kx. I'm just talking about the magnitude of the forces. We will talk about signs after a while, but for the time being, let's focus on the magnitude of the forces. Okay, so I now have an idea of the forces acting in each of the elements. Now go ahead and draw the free body diagram. So this is my little m over here. I'm not worried about the forces acting in the y direction, so I will leave it as such. Then now as the body moves along the tries to move in this direction, which is the positive direction of x, then this spring force will try to resist it in this direction. So I will have a force kx acting in this direction, and by a similar logic, this damper, if this mass is trying to accelerate in this direction, this damper is going to resist that, and it will resist the motion with a force of c into x dot minus y dot. So this I have accounted all the forces acting on this particular mass little m. The next point is this whole system, this whole particular system is accelerating in the x direction with an acceleration of mx double dot. Let's say that it is accelerating in that direction. Then simply using Newton's second law, we will arrive at this particular expression. Summing up the forces in the direction of positive x mx double dot, then acceleration of the mass is equal to sum of the net forces acting on the system minus kx, because it is resisting the motion in the positive direction of x, and then we have c into x dot minus y dot. So just rearranging the terms, we have this particular expression, which is the governing differential equation of the system. I hope that makes sense. So this is the answer. The key concept is, doesn't matter you have a spring or a damper, the net force depend upon the relative displacement and the relative velocity between the 2 points to which both the ends of the spring or the damper is connected. Thanks for watching.